compound semiconductors. As the name implies, these differ from the elemental semiconductor. Elemental semiconductor, silicon, germanium, diamond, etc. In compound semiconductors, they can be formed by using two or more elements from the periodic table. Okay? Two or more elements from the periodic table. Say, if I talk about 3,5 compounds, if I talk about 3,5 compounds, okay, that means group 3 of the periodic table, one element from group 3 of the periodic table and other element from group 5 of the periodic table, that can be used for the formation of 3,5 compound. Say gallium arsenide, indium phosphide, gallium nitride, indium antimonide, gallium antimonide, and so on and so forth. Okay, all those materials are useful in particular applications, in various applications. Gallium arsenide is band gap is 1.43 electron volt. Indium phosphide is band gap is 1.35 electron volt. What is the band gap of gallium nitride? What is the band gap of gallium nitride? 3.4 electron volt, I think. Yes, 3.4 electron volt. Then indium antimonide. What is the band gap of indium antimonide? 0.17 electron volt. And what is the band gap of gallium antimonide? It is 0.72 electron volt. Okay, so what you find from these values, what you find? You find that there is a material, say indium antimonide, whose band gap is very less, 0.17 electron volt. So that material can be used for application in which region? Infrared region. Obviously, if the band gap is less, the region of application will be in the infrared region. Similarly, say gallium nitride, it is 3.4 electron volt. Which region it can? 3.4 is basically UV or in blue. In blue also, that means in visible region. Similarly, gallium arsenide 1.43, it is in the which region? It is also IR. 0.17 is far infrared. 0.17 is far infrared and 1.43 is infrared. So that means a large number of compounds or semiconductor materials are there in compound form in 3-5 groups, which can give you emission in the region from far infrared to ultraviolet, say gallium nitride. The advantage of this compound is that they can be made p type as well as n type. Unlike wide band gap materials, where this doping is very difficult to make. Obviously, for gallium nitride doping difficult to make, because gallium nitride is, though it belongs to 3-5 group, it is wide band gap. Why the doping is difficult to make for wide band gap, I shall discuss. Okay, so the advantage is that P and N doping can be done, and at the same time mobility is high. P and N doping easy to make. P and N doping easy to make and mobility is high. So those can be used for various kinds of application, starting from the optical sources to high mobility devices. High mobility, because I have shown you that the for indium antimonide, what is the mobility? the mobility was indium arsenide say 40,000, indium antimonide is 77,000. So, basically high mobility device can be made, unlike in elemental semiconductor. In elemental semiconductor the mobility was not very high. Another important aspect of this material is that they are direct band gap semiconductor. So, one is direct, number 2 is doping possible, number 3 is high mobility, and number 4 is say 0.17 electron volt to 3.4 electron volt for say gallium nitride, 1.7 is indium antimonide. Long range it can cover, right. So, these are the advantages of 3-5 compound semiconductor, and the some of the names are gallium arsenide, indium phosphide, gallium nitride, indium antimonide, gallium antimonide, indium arsenide, etc. Indium arsenide, etc. What is the band gap of indium arsenide? It is 0.36 electron volt. So, you can get narrow band gap, you can make medium band gap, you can make wide band gap materials in 3-5 semiconductors, which is not possible for elemental semiconductor. And another application of this compound semiconductor is that particularly this gallium arsenide, indium phosphide, etc., those are available for epitaxial growth substrate. For epitaxial growth, you know that a substrate is required on which the growth takes place. Just now we have discussed about the substrate and the layer. So, layer means basically the epitaxial layer, the very thin layer of single crystal. In bulk you cannot go beyond say 300 micron, 400 micron, but in epitaxial you can grow as small as say 1 nanometer, 2 nanometer thickness, 4 nanometer, 10 nanometer thickness. That is not possible using bulk. So, if you want to grow very thin layer of single crystal, very thin layer of single crystal, so these are done by epitaxial growth technique, epitaxial growth technique, and for all epitaxial growth you need a substrate. And this gallium arsenide, indium phosphide are the most important two materials which are used as substrate in epitaxial growth of 3-5 compound semiconductors. These are the 3-5 semiconductors. Now, if I talk about say nitrides, 3-5 nitrides, you see that indium nitride it is 2 electron volt, aluminium nitride it is 6.3 electron volt, and gallium nitride it is 3.4 electron volt. What you find from this data? This indium nitride is 2 electron volt, gallium nitride is 3.4 electron volt, and aluminum nitride is 6.3 electron volt. What you find? That if you grow indium gallium nitride, if you grow indium gallium nitride, indium gallium nitride, you can tune the band gap from 2 electron volt to 3.4 electron volt. Just by changing, say it is x, it is 1 minus x. It is x, it is 1 minus x. You can tune the band gap from 2 electron volt to 3.4 electron volt. Or if you change that indium gallium aluminium nitride, what you find? You can tune the band gap from 2 electron volt to 6.3 electron volt, very large band gap, which covers particularly the visible region, because there are many applications particularly the light emitting diode application or the light in, if you go to Japan, you will find that they have been using light emitting diode for their street light, flat panel display for their street light. And now you know that the bulb has changed to incandescent lamp. Now it is being changed to LED lamp. In the market you will find that within next 2-3 months LED lamp will come. Why? The advantage is that it consumes less power. Now the people have been trying to save energy. So in that direction you need to make very good light emitting diode and a panel of light emitting diode, 10, 20, 100 light emitting diode, because the intensity of one light emitting diode is not very high. So if you want to glow this whole room, if you want to light this room, then say 100 LEDs are required, good LEDs, and different colors, particularly the white color. And you know that the white color is very difficult to make, because the 3 components of white is that the RGB, red, green and blue. We have discussed the red and green, which are the materials using which red and green is used, is fabricated. Gallium phosphide, gallium phosphide. But at that time you have seen that I have not talked about any blue LED, because gallium phosphide is not used for making blue LED. Blue LED is used gallium nitride, silicon carbide, aluminum gallium nitride, indium gallium nitride. These are nitride semiconductors are used. And using nitride semiconductors, if you can zeroing on blue and you have red and green already, so that means you can make white light. That means you can make white light. In that sense, these 3,5 nitrides are very important material. Only blue can be made using them. So very difficult, it is very costly also, because of processing technology and doping. PN junction is very difficult to make. So white light can be made out of red, green and blue. Red and green is available in the market, blue is from 3,5 nitrides. So now you can make white light out of those 3 LEDs. That is mostly used for street lighting and other room lighting, etc., apart from the flat panel display. Okay. And apart from these 3,5 nitrides, there are other materials, say gallium arsenide, aluminum gallium arsenide. Gallium arsenide, aluminum gallium arsenide. Gallium arsenide is 3,5, aluminum gallium arsenide is also 3,5, but that is known as ternary. Gallium arsenide is binary, this is ternary, that means 3 elements are involved. And say indium gallium arsenide phosphide, it is known as quaternary. So that means 3,5 compound semiconductors can be grown as binary, ternary or quaternary. So when you go for ternary or quaternary, that means some band gap engineering is made. That means you are changing the band gap of the material. What is the band gap of gallium arsenide? It is 1.43 electron volt. What is the band gap of aluminum arsenide? Aluminum arsenide 2.1 electron volt, aluminum arsenide 2.1 electron volt. So that means if you make aluminum gallium arsenide, you can tune the band gap from 1.43 when x equals to 0, it is and when x equals to 1, it is 2.1 electron volt. That means you can tune the band gap from 1.43 to 2.1. Similarly, if you have say indium gallium arsenide and gallium arsenide. Indium arsenide band gap is how much? 0.36 and gallium arsenide 1.43. So, if you make one indium gallium arsenide for x equals to 0, it is 1.43. For x equals to 1, it is 0.36. So, that means you can tune the band gap from wide range from 0.36 to 1.43 electron volt. So, that is also possible using the compound semiconductor. You can tune the band gap. That is not possible using elemental semiconductor. So, you can play around. The area is large compared to elemental semiconductor. Apart from that, they are direct band gap, their mobility is high, and you can tune the mobility. They can be doped both p and n type. That is advantage. But there are disadvantages also. The disadvantages are, one of the main disadvantages are that like silicon, it cannot be oxidized. SiO2 is very easy to make, and SiO2 is also insulating in nature, and it is widely used for processing. For gallium arsenide or aluminum gallium arsenide or indium phosphide, etc., you cannot make this oxidation, because you see that in this view graph, you see that the dangling bonds I have shown you, these are the surface, this is the bulk. So, in bulk you see that all the bonds are saturated, but at the surface these bonds are unsaturated. That means they are open. So, they can take up any material, particularly the aerial oxygen. So, gallium arsenide, if this material is gallium arsenide, this gallium oxide will not be formed very easily. There will be some oxide layer obviously, but not exclusively gallium oxide like silicon SiO2. Okay. So, that is disadvantage for this gallium arsenide or compound semiconductor. One part is oxidation. Another important disadvantage is that processing technology. Silicon you can dope very easily, you can diffuse, you can ion implantation is done, photolithography, all processing technology is very matured. You can handle large wafer. In gallium arsenide or indium phosphide you cannot make. Large wafers are very difficult to handle because they are brittle in nature, they are very soft. So, those are the disadvantages. Though it has many advantages, it has disadvantages as well. Another disadvantage is the cost. The cost is very high, almost 5 to 6 times higher than silicon. If you purchase one silicon wafer, say it cost is say 12,000. If you cost gallium arsenide wafer, it cost will be 50,000. 3 inch, it is almost 50,000. In some cases it is higher than that. 3 inch wafer just compared to gallium or silicon is very cheap in that sense. Okay, and another thing is that apart from this 3,5 compound, you have say 2,6 compound, 2,6. That means one element from periodic table 2, one element from periodic table 6, say zinc and cadmium, and in 6 you have oxygen, sulfur, selenium and tellurium. Group 6 oxygen, sulfur, selenium and tellurium. That means zinc oxide, zinc sulphide, zinc selenide, cadmium oxide, cadmium sulphide, cadmium telluride, etc. So, those are the 2,6 compounds. Here you see that problems, major problems with these materials are, except cadmium telluride, except CDT, both P and N type doping is not available. Both P and N type doping is not available. Mostly those are P type in nature, N type in nature. Say zinc oxide, it is N type. Cadmium sulfide, it is N type. Zinc sulfide, selenide, it is N type. Almost all of them are N type except zinc telluride, which is P type. Zinc telluride is P type. All other 2,6 compounds are N type in nature, except cadmium telluride, which is available as both N type and P type. So, this is the limitation of 2,6 compound. This is a limitation of 2,6 compound in the sense that both type of doping is not obtained. So, unless doping is not obtained, then what is the difficulty? Difficulty is that you cannot make a device. The primary requirement for fabrication of a device is a p-n junction. There are other avenues, not that these 2,6 compounds are not used, they are used, but not very easily. Silicon p-n junction is very readily made, gallium arsenide p-n junction is very readily made, but these 2,6 compounds, zinc oxide or cadmium sulfide or zinc selenide or zinc telluride, they are not readily made p-n junction. That is disadvantage. Why such thing happens? Why there is a problem of doping? What is the difficulty? Difficulty is that you heard the term stoichiometry. You heard that, particularly the chemistry student, you know that what is this? What is this stoichiometry?
Chemical balance.
Yes, chemical balance. So, when you make a material, definite proportions of materials are there, and if you take the ratio, it gives you a law of definite proportion. That means, say zinc oxide, zinc to oxygen ratio is 1, 1:1, but actually it is not there. But actually it is not there. Here in zinc oxide, the oxygen becomes 0.95. That means there is some deficiency of oxygen in zinc oxide. Say FeO, ferrous oxide. The exact formula is not FeO, it is Fe 0.95 and O. So, that means if you take the ratio, it is not a natural number, 1/0.95. Here you see that it is 0.95/1. Ideally it should be 1/1, but there is a deficiency of oxygen here, there is a deficiency of iron here. So, some materials are there, when you grow, because of thermodynamic consideration, there will be deficiency of one particular element in it, and that is the reason that it is known as non-stoichiometry. So, what we find in case of zinc oxide? You see that in case of zinc oxide, there is a vacancy of oxygen, and because of this oxygen vacancy, it acts as N type. It acts as N type. So, if you try to dope it, say P type, what will happen? The dopant will be compensated, because already there is vacancy, already there is vacancy. So, the dopants will be compensated by the vacancies. So, first as you go on increasing the doping concentration, there will be compensation. This is known as a self compensation, because there is enough vacancies there inside the material. And finally, what will happen? Finally, when all the vacancies will be full, so there will be no place for it. So, that will be solid solution, there will be no doping, because we have discussed during our doping and diffusion that either it must occupy the interstitial position or it must occupy the vacancy position, defect positions. If there are no positions, it will, yes, where it will be accommodated. So, then that will be a solid solution, that is not doping. So, that is the reason, because of this non-stoichiometry, in natural production it is non-stoichiometry in nature. There are oxygen vacancy, and there are different types of materials, say in zinc telluride, then maybe there is zinc vacancy or tellurium vacancy. So, as you go on increasing the doping concentration in it, it will first compensate it. Because of self compensation, the effect of doping will not be observed, will not be visible. Such kind of thing is not there in case of silicon or say gallium arsenide or indium phosphide. So, that is the reason that these materials cannot be doped very easily. There are techniques people have been trying. I have also tried to dope zinc oxide p type, we have done, but the problem is stability. After 2 hours, 4 hours, after 2 days, it will come to back to square one. So, there are several problems people have been trying. So, these are the major problems associated with the 2,6 compounds. But 2,6 compounds are, you see that these 2,6 compounds are widely used for particularly some of the applications in optical applications. Optical applications. And what are the applications? One is say zinc sulphide. When you dope with silver, or zinc sulphide when you dope with Mn, this is CRT, cathode ray tube, that means display application. Display application. And mercury cadmium telluride, this is IR detector. Zinc selenide and zinc sulphide, protective windows. Then cadmium telluride, nuclear radiation detector. Then I have cadmium sulphide and cadmium telluride also. These are used for solar cells. So, these are the various types of applications that can be made out of 2,6 materials. Mostly those are optical in nature. Silver and manganese doped zinc sulphide are used for a display device in cathode ray tube, and the cathode ray tube there is a thin film coating of zinc sulphide or zinc silver or Mn doped. And in cadmium telluride, mercury cadmium telluride, this is very important application for IR detector, infrared detector. infrared imaging. That means this is a very ambitious project of DRDO that is handled by SSPL Delhi Solid State Physics Laboratory, and they have been trying to make HGCDT detector. Some success they have got. So, this is basically to map the battlefield at night, to map the battlefield at night when there will be no light. So, there will be object or metallic object will be there, say tank or that type of things. So, infrared will, some source will be there, infrared source, those infrared light will be reflected back from the surface of the tank or metallic objects, and then there will be a camera or detector which will detect the positions or the locations of the tanks, etc. So, that is very ambitious project for Indian military, and they have been trying in SSPL. This is very important material, cadmium, HgCdT, mercury cadmium telluride. And this zinc selenide and zinc sulphide, it is the protective windows or the optical elements. This cadmium telluride, it is nuclear radiation detector, say gamma detector, etc. Or in case of say CDT, it is used for solar cells also, and cadmium sulphide is also for solar cells. So, these are very important material 26, though it has some inherent limitations of doping, etc., because of its band gap, nature of the band gap. And another important material which we should discuss is the zinc oxide. Zinc oxide is one very important material. Its exciton binding energy is 60 milli electron volt, 60 milli electron volt exciton binding energy. What is the room temperature binding energy generally? 26 milli electron volt, 26 milli electron volt, thermal energy basically. So, 60 means 2.5 times, almost 2.2 to 2.3 times. So, that means even at room temperature, the value is higher than room temperature. So, even at high temperature or even at room temperature, zinc oxide can be used for fabrication of light emitting diode or laser sources. That is very important material, zinc oxide. But problem is that it is not stable and doping is not very easily be made. So, that is the reason that zinc oxide has no commercial applications right now, but the people have been trying. Another thing is that if you add some magnesium, that means ZNO, you add some magnesium zinc oxide, MgZNO. This magnesium zinc oxide, it is, if you add some magnesium, then you will find that the band gap has increased. What is the band gap of zinc oxide? It is very high. Zinc oxide is 3.37 electron volt. 3.37 electron volt to, if you add magnesium zinc oxide, then it will be almost 6 electron volt. That means a very large band gap can be tuned from 3.3 to 6 electron volt. And what is the main application of this region? What is the main application of this region of 3.37 to 6 electron volt? It is ultraviolet. It is ultraviolet region, and ultraviolet is used for which application? What is the application for ultraviolet? Storage device. CT, basically storage device, because the storage capacity is almost inversely proportional to 1 by lambda to the power 4. We have discussed in my first lecture. It is almost varies as 1 by lambda to the power 4. So, if lambda decreases, the storage capacity increases. So, present generation storage capacity is red. Then if you can go to blue or then ultraviolet, then manifold it will increase, and I have introduced your Blu-ray device, Blu-ray disc. So, that is very important thing that ultraviolet can be used. Then there are say 4,6 compound. Four 6 compound is lead sulphide, lead selenide and lead telluride. Lead sulphide, lead selenide and lead telluride. Lead sulphide is 0.37 electron volt, lead selenide is 0.27 electron volt and lead telluride is 0.29 electron volt. These are the basically narrow band gap material. This band gap you see that the very less, it is 0.27, 0.29 and 0.37. It has high carrier mobility. High dielectric constant. And direct energy gap. And another important aspect of these lead compounds, lead semiconductor, is that it has positive temperature coefficient of band gap. What is positive temperature coefficient of band gap? Yes, generally what happens? Generally at room temperature, say the band gap value is 1.1 electron volt for silicon. If you decrease the temperature, the band gap will increase, or if you increase the temperature, the band gap will decrease. That means generally negative temperature coefficient is there, except these materials, except these lead materials, that means 4,6 compounds. In these 4,6 compounds, if you increase the temperature, band gap increases. That is the unique feature of this 4,6 compound. In other materials, you will not find this thing. Exactly the opposite happens. Another advantages are that it has high carrier mobility, its dielectric constant is very high, it has direct band gap. So, some advantages are there, but positive temperature coefficient is there, and its main application is in the detector material. That means infrared detector, because you see that the temperature, the band gap is very low. So, infrared detector, and another application is thermoelectric application, because lead telluride or lead sulphide, these are used for thermoelectric application. So, many materials are there, and these compound semiconductors are used for different kinds of applications. Next, we shall concentrate our discussion on, say, narrow band gap semiconductor. Narrow band gap semiconductor, say indium antimonide, it has 0.17 electron volt. Then indium arsenide, it has 0.36 electron volt. Then lead selenide, it has 0.28 electron volt. Lead telluride, it has 0.31 electron volt, and so on and so forth. There are other materials also which can be say gallium antimonide, it is 0.72 electron volt, etc. So, these are all narrow band gap materials, and these narrow band gap materials are almost all are in direct nature. Remember that if the band gap is direct in nature, then it can be used in optoelectronics. That is special point. It can be used optoelectronic for detector as well as for sources. There are other constants like doping, etc., but first constant is that it must be direct. Then you can cross the minimum barrier. And these are basically materials which are used for infrared detector. And say lead selenide and lead selenide, lead sulphide and lead selenide, you see that the band gap is so less that it is 0.28 electron volt. You will find that it can be used for 1 to 6 micron infrared detector, IR detector. What is 1 to 6 micron? 1 to 6 micron is it can absorb 1 micron to 6 micron wavelength light. 1 micron to 6 micron wavelength light. Where it is used? Such micron 1 to 1.5 micron is, we know that it is in fiber optic communication. 1 to 1.5, say 1.3 micron, 1.55 micron, we have discussed it is used in fiber optic communication. But this 3 micron, 4 micron, 5 micron, 6 micron, yes, in remote sensing applications, in say atmospheric, there are the different kinds of gases, etc., affluent gases. So carbon monoxide, carbon dioxide, sulfuric SO2, etc., sulfur dioxide, etc. So for detection of those gases, etc., this high infrared region is used. Now the important part is the wide bandgap semiconductor, where we shall devote some time. Wide bandgap semiconductor. Wide bandgap materials. One is that it has high thermal conductivity. High thermal conductivity. High saturation drift velocity. High electric background field. And number 4 is that superior physical and chemical stability. Okay, so these are the 4 important points or the common property of wide bandgap materials. Any wide bandgap materials has these 4 common property. One is that it has high thermal conductivity. Number 2 is that it has high saturation drift velocity. Number 3 is that it has high electric background field. And number 4 is that superior physical and chemical stability. Apart from that, the band gap is wide. Apart from that, the band gap is wide. Now, where we use those materials? What are the specific applications of these wide band gap materials? One is that is high thermal conductivity. What is the advantage of high thermal conductivity? Heat dissipation, right. So that means you know that for particularly high power applications, high power transistor, or in say thyristor type of application where high current is involved, the circuit basically is heated. Then there is heat sink. There is heat sink, metallic heat sinks are there. Generally aluminum is used or copper is used. But since their thermal conductivity is very high, so they dissipate the heat very easily without taking help of other kinds of heat sink. Or if you can use heat sink, then it will be, if you can use heat sink, then it will be another type of advantage. But you see that this high thermal conductivity makes it the most important heat resistance device. Then high saturation drift velocity. What is high saturation drift velocity? What is high saturation drift velocity? Then what is the why it is important? What is the implication of this velocity? Maximum? No, actually Vd equals to mu e. Vd is the root velocity, mu is the mobility, is the electric field. So, if you plot E versus Vd, then first it increases, then it saturates, then it saturates. We want that the velocity saturation comes at very high electric field. Say if this electric field is say E1, we want that it comes at say E2 or E3. Okay. So, because of this thing, we prefer that the saturation root velocity is becomes high. This is the saturation, onset of saturation here. Now, this if you plot say this curve, and then second one is like this one, and third one is say this one. So, you see that the saturation values are E1, E2, E3, E4 etc. So, high saturation root velocity means if the root velocity saturates at high electric field. This is particularly important for high power device. This is particularly important for high power device, because for high power the electric field associated is very high, and if the root velocity saturates, then some of the properties you will not find, some of the applications you will not make. If it saturates in a very low field, then for in high field it will not work basically, right, because we want that the electrons will be as movable as in the low field region. See, if the root velocity is say Vd1 at electric field E1, we want that at electric field E2 it must be Vd1 at least, right, but it becomes, if it becomes greater than Vd1, then it is better. So, that means the saturation must come not in the early stage, but in a later stage, so that you can make use of this phenomena for particular application. Remember that this wide bandgap material is used for high power devices, high power transistor, in electrical devices. And another important aspects of this saturation root velocity is that high frequency application, that is also very important. That means say RF, if you would like to make one RF amplifier, radio frequency amplifier, or microwave sources, then the saturation root velocity must be very, very high. Otherwise, the operation of the frequency limit, that means if you plot the frequency versus amplification, then you will get this kind of a curve, that is its bandwidth. It is say it is f2, it is f1. So, f2 minus f1 is the bandwidth of this material. So, if the bandwidth is becomes very large, if you want that the bandwidth becomes large, then the root velocity must be very, very high. The saturation should not come at very early stage. So, that is a important parameter. Another is high breakdown field that we have discussed. Then what is this breakdown field? What is breakdown? Breakdown, you know that if you consider the p-n junction characteristics, IV characteristics of a p-n junction in the reverse bias, what you will find? In the reverse bias, what you will find? Basically, it will be, then it will break down. This is the point where the breakdown occurs, right. Now, if your breakdown occurs at this point, then it is known as the early breakdown. It is known as the early breakdown. What we want actually? We want that the breakdown occurs at in a later stage in very high voltage, say it is -1 volt, then -2 volt, -3 volt and so on 10, 15, 100, 50, it better if it becomes 220 your line voltage. So, that is very important thing, that if you use a silicon device, then the breakdown field is within 5 to 10 volt, minus 5 to 10 volt. But if it is a wide bandgap material, then its breakdown field is 50 to 60 volt. Some of the applications are there where in the positive cycle it is okay, positive voltage is going, but in the negative cycle the reverse voltage will be there in the PN junction, making it a reverse bias, and at that point if breakdown occurs, then your circuit will be broken, your purpose will be failed. So, that is the important thing which we should consider for wide bandgap semiconductor. So, these are the 4 important points. One is high thermal conductivity, one is high saturation drift velocity, high electric breakdown field and superior physical and chemical stability. And what are, can you name some of the wide bandgap semiconductors? Nitrides are wide bandgap semiconductors, not all nitrides, but some of the nitrides. Then silicon carbide is a wide bandgap semiconductor, right, silicon carbide. Say some of the name of the wide bandgap semiconductor is diamond, carbon, it is 5.5 electron volt, it is diamond. Then silicon carbide has 2 band gap, one is 3, another is 2.3 electron volt. Why silicon carbide has 2 band gaps? Why silicon carbide has 2 band gaps? That why? Because silicon carbide can be crystallized in 2 different forms. One is cubic, another is hexagonal. Okay, one is cubic, another is hexagonal. So, if it is hexagonal, then its band gap is this. If it is cubic, then its band gap is not in true sense is wide. Then aluminum nitride, it is 6.28, gallium nitride, it is 3.44, zinc sulphide, it is 3.68, zinc selenide, it is 2.7. So, these are the wide band gap semiconductors which are readily available, and it is used also in different kinds of applications. Generally, you can greater than 125 degree centigrade you can use those devices, greater than 125 degree centigrade, and it will consume power. So, heat will be there. So, heat dissipation will be in a faster rate for wide bandgap semiconductor. So, wide bandgap semiconductor is very useful materials in electronic industry, particularly for high power devices, and where that heat conduction is required and where your this high temperature withstand is required, then this is very important material. And also one important material is a silicon carbide or nitride, that can be the band gap can be tuned up to this visible range. That is also important thing, that blue material can be used, blue device can be used using silicon carbide or gallium nitride. Okay, silicon carbide or gallium nitride, blue LED or blue laser is used, and for say white light, fabrication of white light, these materials is very important. So, if we conclude our discussion that first we have taken that elemental semiconductor, next we have considered the compound semiconductor. For compound semiconductor, we have say 3-5, then we have 2-6, then we have lead materials, that is 4,6 compound. Then we have this wide band gap, then narrow band gap, etc. In wide band gap, you see that it forms a different group. Silicon carbide, which group? Silicon carbide, which group? 4,4, right, 4,4. Then carbon or diamond is group 4. Silicon carbide 4. Aluminum nitride 3,5. Then zinc sulfide 2,6. This is also 2,6. These are all 3,5. This is all 3,5. So these are the various groups. That means not necessary that a particular group is useful. Almost all materials are useful and they have definite application. Obviously, these wide bandgap semiconductors are not used for making integrated circuit like silicon, obviously, but they have some other applications. 3,5 semiconductors are not used for optoelectronic are not used for integrated circuit. They are used for optoelectronic devices. So they have different kinds of applications, and I shall show you during our discussions that many materials are there which are used for solar cell applications, or a large number of materials we use for making very good solar cell or light emitting diode or laser, etc. Okay? Thank you.